Welcome back. In this video, we'll delve into a couple of examples to enhance our understanding of objects in motion, on surfaces with friction. In the first example, we'll examine two objects connected on either side of a string, sliding on two inclined surfaces. The angles of inclination of the surfaces to the horizontal are 30 degrees, and 15 degrees respectively. The object with a mass of 10 kilograms is on the surface with a 15-degree inclination, while the object with a mass of 20 kilograms is on the surface with a 30-degree inclination. Both contacting surfaces have a coefficient of kinetic friction of 0.1. Our objective is to determine the acceleration of the two objects, and the tension in the rope as it slides along the surfaces. For simplification, we can assume that the mass of the pulley and the string are negligible, and the pulley is freely rotating. Let's start by sketching a free body diagram, to understand the forces acting on both objects. A free body diagram is essentially a vector diagram, illustrating all forces, including reactions, acting upon an object. Once you've drawn the free body diagram for an object, you can isolate and analyze it independently from the rest. However, when drawing a free body diagram for a combination of objects, it's essential to disregard any internal forces acting between the objects considered as a group. If you need a more detailed explanation, or are uncertain about the process, feel free to check our last video, where we delved deep into drawing a free body diagram. I've provided a link to that video below for your convenience. It should help clarify any uncertainties you might have. Now, let's proceed to the next step, where we'll apply Newton's second law to determine the acceleration of the objects. Taking the direction of acceleration, as indicated in the diagram, as positive, we'll apply Newton's second law to the entire system. Following this, we'll focus on one of the objects, applying Newton's second law to calculate the tension in the rope. But before we dive into Newton's second law, it's essential to resolve all the forces in the direction of acceleration, and perpendicular to it. In this instance, our focus will be on resolving the weight vectors of the two objects, because it's the only vector not aligned with either of the directions. On the screen, you can see the two weight vectors after we've resolved them in the direction of acceleration and perpendicular to it. Don't skip this step, it lays the groundwork for problem solving. In this specific example, Object A slides down along the plane, while Object B moves up on the plane. The frictional force opposes this motion, and acts in the direction opposite to the movement of the two objects. These forces are represented as F of R A and F of R B, highlighted in yellow. The expression provided explains the connection between the normal force, and the kinetic frictional force, using the coefficient of kinetic friction in the context of the two objects sliding on the surface. To figure out the normal force for Object A, we're looking at the net force in the direction perpendicular to the acceleration. Since Object A doesn't move in that direction, we end up with this equation for its normal force. Solving this equation gives us the value you see on the screen for the normal force of Object A. Plugging in this value along with the coefficient of kinetic friction into the expression at the top, yields the frictional force opposing the motion of Object A, which is calculated to be 16.97 Newton. Continuing with the same steps we followed for Object A, we can determine the normal force of Object B, as shown on the screen. Using this value of normal force, along with the coefficient of kinetic friction, we can calculate the frictional force opposing the motion of Object B as 9.47 Newton. Next, let's apply Newton's second law in the direction of acceleration for both objects together, as a system to determine the acceleration. Starting with Object A, and moving along the direction of acceleration or the string, we derive this expression. It's important to note that tension is excluded from this expression, as it cancels out when considering the two objects together. Also, make sure to add up all the masses contributing to this acceleration, treating mass as a scalar quantity. By substituting the calculated values for F of RA and F of RB, we end up with an equation that we can solve to determine the acceleration of the two objects. The calculated acceleration is 1.54 meters per square second. Next, we can choose any one object and apply Newton's second law to find the value of tension. Applying Newton's second law to object A in the direction of acceleration yields this expression for tension. We can substitute the previously calculated values for acceleration and the frictional force opposing the movement of object A into this equation. Upon solving this equation, we find the tension in the string to be 50.22 Newton. I hope this explanation was clear. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Okay, so in this example, we're diving into the motion of these three objects. I picked this one on purpose to make Newton's second law more tangible for you, and to really get a grip on how it works when applied in one go. Check out the screen, you'll see two objects at both ends of a rope, and there's a third object attached to the middle of the rope. This object at the center is on a rough surface, and it's got a friction coefficient of 0.2. Now, let's check out the weights of these objects. The one hooked to this end of the rope has a mass of 10 kilograms, and similarly, the object on the rough surface also carries the same weight. However, the object attached to this end of the rope is a bit heavier, tipping the scales at 20 kilograms. This animation gives you a clear picture of how these objects behave when they're simply allowed to fall freely. In this scenario, we need to dive into some calculations to determine the acceleration of these objects and the tension on each side of the rope. As in previous scenarios, we'll maintain the assumption that the rope and pulley are weightless, and the pulley operates smoothly. Now, let's move on to the next step, which involves sketching the free body diagram to gain a clearer understanding of the forces influencing each object. I recommend pausing this video for a few seconds to draw the free body diagram. I'm confident it should be a breeze, especially considering we've tackled more intricate systems with ease in the past. What you're seeing on the screen is the free body diagram. I'm confident that you've created a diagram similar to this one, which is fantastic. Let's take a moment to grasp this diagram. I have marked the weight vectors of the three objects in the direction of gravity. These vectors are shown in white. The tensions in the two ropes are labeled as T1 and T2. Now, why did I use two different notations for these tensions? It's because these two ropes are connected to object B, and there's a force opposing the motion of object B, which is the frictional force. Therefore, the tension in the ropes on either side of object B will not be the same. I have labeled the frictional force opposing the motion of object B as F of RB. Object B rests on a surface that exerts a force on it, known as the contact force, or the normal force. This force is denoted as R of NB. Both the normal force and the frictional force are depicted in yellow. This sums up the elements in the free body diagram. However, I've also incorporated the acceleration of each object. This inclusion assists us in identifying the direction of motion and the relevant direction to consider when applying Newton's second law. It's crucial to remember not to include forces that the object exerts on its surroundings when drawing a free body diagram. The next step is to identify the external forces acting on the three objects, as we are going to apply Newton's second law to all the objects simultaneously. In this free body diagram, besides the tension in the ropes, we need to take into account the remaining forces. However, before we put Newton's second law into action, we must determine the frictional force resisting the motion of object B. we can use this expression to calculate the frictional force. Since object B remains stationary in the vertical direction, the net force in that direction must be 0. This implies that the vector sum of the weight of object B and the normal force equals 0, providing a value for the normal force as 98 Newton. Subsequently, we can utilize the friction formula to compute the friction that opposes the motion of object B. Alright, let's now apply Newton's second law to determine the acceleration of these three objects. But what exactly is this F net in Newton's second law? It is the vector sum of forces in the direction of acceleration. Now, considering these three objects move in three different directions, how do we calculate the net sum? In problems of this kind, where the direction of acceleration is altered by a pulley and connected by an inelastic string, we consider the direction of acceleration of individual objects as the positive direction. Consequently, we calculate the vector sum of forces applied to all the objects, considering the direction of acceleration specific to each object as the positive direction. Let's begin with object A. The weight of object A acts in the opposite direction to acceleration, so we consider it as negative. The tension, on the other hand, aligns with the direction of acceleration, so we take it as positive. Now, we mentioned earlier that we typically don't consider tension as it's an internal force. However, rest assured, it will cancel out by the time we complete listing the forces in the direction of acceleration. Moving on to object B, let's identify the forces in the direction of acceleration. We have the tension T2 of the rope connected to object C, which aligns with the acceleration direction. However, the tension T1 of the rope connected to object A, and the frictional force opposing the movement of object B, are in the opposite direction to acceleration. Therefore, we take T2 as positive, but T1 and F of RB as negative vectors. Now, regarding the weight vector of object B. It is in a direction perpendicular to the acceleration. Therefore, the component of the weight vector in the direction of acceleration is 0. Consequently, we do not consider the weight of object B in this context. Let's shift our focus to object C. In this case, the weight vector aligns with the direction of acceleration, so we consider it as a positive vector. However, the tension T2 is in the opposite direction to acceleration, so we take it as a negative vector. With that, we can calculate the net force in the direction of acceleration. As mentioned earlier, the tensions in the ropes are not included in this expression. When we sum up all the forces, the tensions of the rope cancel out, leaving only the external forces. Ultimately, we can calculate the net force as 88.2 Newton. When calculating the total mass, we account for the mass of all the objects experiencing the acceleration. As mass is a scalar quantity, we simply sum up all the masses. In this example, the total mass moving with the same acceleration is given as 40 kg. Now that we have all the information, we can calculate the acceleration of the system using Newton's second law. Substituting the calculated values for net force and total mass into the expression, we obtain the following equation. Solving this equation yields an acceleration of 2.2 meters per square second. I trust the explanation on calculating acceleration was clear. Now, let's delve into determining the tension in the two ropes. In this scenario, we need to apply Newton's second law to a specific object since tension is an internal force. Although we could select any of the objects for this purpose, considering both objects A and C allows us to calculate the values for the two tensions using a single expression. So, let's start by considering object A and applying Newton's second law in the direction of acceleration. The expression derived from applying Newton's second law is as follows. Solving this equation provides the value for tension in the rope as 120 Newton. Similarly, we can apply Newton's second law to object C in the direction of acceleration. This results in the following expression. Solving this expression yields the tension in the rope as 152 Newton. Thank you for watching this video all the way through. I trust you found it informative and beneficial. If you haven't already, kindly consider subscribing to the channel. Until our next video, take care and goodbye.